This project is on woodpeckers by Kinsey Alexander,
Austin Ionetti,
Natalia Seepley,
and Zach Wright.
Background. The focus of our project is woodpeckers. Woodpeckers are a type of bird whose various species may be found around the world. They are known for their pecking sound, which is called drumming. Their different species vary largely in size, yet all produce the identifiable drumming sound. The size variation can be anywhere from 7 to 50 centimeters long. The weight variation can be between 7 and 360 grams. The dynamic system we are going to investigate within this video is the pecking of a valley oak tree by an acorn woodpecker. The average length and size of an acorn woodpecker is 21 centimeters and 85 grams. A valley oak tree can live up to 300 years and grow to roughly 30 meters. Dynamic system. Based on the frequency that the woodpeckers strike its beak into the tree and its precision, a hole is produced in the tree. This natural system demonstrates the same mechanics as a jackhammer drilling into the ground.
As with many systems, the governing equation of motion is Newton's second law: force is equal to mass times acceleration. Specifically, this is transformed to satisfy harmonic motion with force and damping terms. This equation describes the oscillation of the woodpecker's drumming as it moves its head back and forth. The properties of each subject must be taken into account when analyzing the motion of the system. The tree provides a stiffness and a majority of the damping coefficient for the governing equation. Analyzing the woodpecker, we see that it has its own contained dynamic system that allows it to take the constant impact. Within the tree to woodpecker system, the woodpecker acts as the main force factor and provides a constant drumming frequency and striking velocity. To properly analyze the motion within the system, a reference frame must be chosen. There are an infinite amount of frames we could choose. However, the two most logical frames for the purpose of studying the drilling of a woodpecker are centered either at the point of impact on the tree or at the center of the woodpecker's rotation.
The woodpecker uses its talons to latch onto the tree and rotates about a point close to its feet. As seen in the figures, its motion is similar to that of a pendulum swinging and hitting a wall. As mentioned earlier, the properties of a woodpecker create a dynamic system on its own. This can be analyzed as a system of springs and dampers. The force exerted by the beak on the tree is shown on the far right of the diagram. To protect its brain, the woodpecker uses several body parts to dampen the impact it feels. As defined by its properties, the woodpecker's beak provides some damping and deforms slightly, acting like a spring. Young's modulus plays a crucial role in determining the overall force experienced by the woodpecker. Young's modulus describes the resistance a material has to being elastically deformed, and the individual bones in a woodpecker can be approximated as springs, with their spring constant proportional to their respective Young's modulus. The damping coefficient of each body part is experimentally determined, and the initial impact travels through the beak of the woodpecker, then undergoes further damping by the hyoid bone, while finally reaching the skull and cerebral spinal fluid, where it gets completely dispersed. The woodpecker then retracts to strike again.
A closed-loop system is displayed in the figure. Following the feedback loop, the woodpecker uses visual inputs for reference. From there, its brain can be viewed as the control deciding the system input. The system input is the applied force to the tree, and the output is the restoring force the woodpecker feels on its beak. In addition, a hole has been produced and may be visually inspected. The loop repeats, and the woodpecker adjusts its motion based off of the system outputs. This can be observed when watching a woodpecker drill. As seen in the video, the woodpecker continually makes minor adjustments to where it is drilling. As it drills, the woodpecker takes in many different inputs to adjust its position and force exerted. It takes in visual inputs from its previous peck to choose its next pecking location. It also experiences the restoring force on its beak, as mentioned before, and biologically knows how to immediately adjust for the next impact. At the same time, the woodpecker is able to maintain a steady frequency while continuously adjusting. As such, the system of a woodpecker drilling into a tree is continuous. Although it may seem discrete as the woodpecker takes breaks in drilling, it has been observed that the woodpecker continuously changes its outputs of drilling position and velocity. It does not maintain the same motion for a set period of time. Finally, one may ask, how do you calculate the performance of the system? For the woodpecker, the answer is easy. Does the acorn fit in the hole? If so, it has completed its job. In general, the performance of the system can be calculated based off the efficiency leading to the completion of drilling. In addition to being determined by the properties of the hole, one may also look into the energy exhausted by the woodpecker. If the job was finished with energy left to spare, the woodpecker would be viewed as an efficient driller.
Thank you for watching. We hope you enjoyed our presentation.